So we've already talked about random variables in general, about their distributions and about their means, also called expected values, and also about their standard deviations. And those things work for any kind of discrete valued random variable. However, it turns out that there are some very special cases of random variables that arise naturally in industrial systems, nature, any kind of study of engineering or science, mathematics, business, finance. And we'll focus on a couple of these here. One's called the binomial and the other is called the normal. Binomial random variables. Binomial random variables. Bi meaning two. Nomial meaning, I don't know, nomial, random variables. Suppose that we know, based on experience by observation, we've done some statistics on it, we just feel confident, we know somehow that Matt makes 90% of all free throws, and the outcomes of his shots are independent. That is, once I've sufficiently warmed up or something, then I make 90%. And regardless of how many I've just made in a row, the next time I take a shot, I have a 90% chance of making it. Independently of the past, independently of the future. All the outcomes of my shots are independent. So suppose I'm about to take 7 shots from the line. In the next 7 shots, and again, these things are done independently. In the next 7 shots, assuming each one has a 90% chance of going in, what's the probability that Matt makes, say, all of them? All of them. Well, the first thing I'm going to do is I'm going to define my random variable of interest. This is an important first step. Define my random variable of interest. Okay, so I'll use an x for this. Say x equals the number of shots in the next 7 that Matt makes. Okay, so note that x will take on a value in the set 0, 1, 2, all the way up to 7, right? That's what this little symbol here means. It means x is in. It looks like a little funny looking E. Don't worry about it. But it means that x takes on a value from this set. That is, x is the number of shots Matt makes, or the number of successful shots in 7. Important first step there is defining this random variable, because it's a lot easier to write this all over the page than it is to keep on writing all of this stuff. That's why we define our random variables. It's because we are lazy. Yes, we don't want to keep writing stuff all over the place. What's that first question ask for? It asks for the chance or probability that x equals 7. Okay, that is, what's the chance that he gets all of them? So if I let m1 be the event that he makes the first one, and m2 be the event that he makes the second one, and so on, then isn't this just like this? It's the chance that he makes the first, and makes the second, and makes the third, and makes the fourth, and makes the fifth, and so on, and makes the seventh. By independence, I can write this as the product of the chances, right? Remember, if I have independent events and I want to know the chance that all of them occur, and if they're independent, I can write that as just the product of the chances of the individual events. Now, each one of these probabilities is the same, isn't it? 0.9 times 0.9 times, and so forth and so on, right? Times 0.9. That's just 0.9 raised to, gosh, how many 0.9s do I have there? 0.9 to the 7th. If I drag up my calculator over here, it's 0.9 raised to the 7th, 0.478 approximately, 0.4783. Okay, it's about 47.83%. Now, I've got a pretty good chance, 90% chance of making any one shot. But to make 7 in a row, I got less than 50% chance of making all of them. Okay, makes sense? Now, what's the next question there? Part B says, what's the chance that he makes exactly 4 of them? Exactly 4 of them. So let me put this in green just because I like green. What's the chance that x is exactly 4? Gosh, I'm not even really sure how to do that yet. But I tell you what I do know how to do. We'll come back to that in a minute. I do know, how to get the chance that he, can we do it like this? Make, not make, not make, not make. Can I write it like that? That'd be okay. This is the event that he makes the first 4 in a row and misses the last 3, right? Again, by independence, this is going to be, guess what? 0.9 to the 4th times 1 minus 0.9 to the 3rd, right? Because I got 4 makes and 3 not makes, 3 misses, 4 hits and 3 misses, right? The chance of hitting is 90%. The chance of missing on any one shot is 1 minus 0.9, right? I got 3 of those. All right, independence means that if you're intersecting events there and you want the chance of their intersection, then you can just multiply the chances of the individual events. I ask a related but different question. What's the probability that I say make, miss, make, miss? Well, let's see. That's going to be 0.9 to the tooth, right, because I got 2 there, and I have 1 minus 0.9 to the, also to the tooth, right, because I got 2 there, and then I got 0.9 to the tooth, right, because I got 2 there, and then I got 1 minus 0.9. Okay, just one of them because I got 1 there, right? 1. Oh, hey, you know what? It doesn't matter what order you multiply. This is 0.9 to the 1, 2, 3, 4. 0.9 to the fourth, and then times 1 minus 0.9 to the 1, 2, 3, right? 1, 2, 3. Hey, guess what? This is exactly the same as this. How about that? Let's do another one. What about the probability that I make, miss, make, miss, make, miss, and then make? Guess what? It's going to be the same thing. By independence again, I can write this as the product, right? It's probability that I make times the probability that I miss times the probability and so on, right? Which is, again, just going to be 0.9 to the, gosh, how many makes do I have? 1, 2, 3, 4 makes, right? And 3 misses, okay? Raised to the third. So it doesn't really matter what order the makes and misses are in. The chance of that event is going to be 0.9 to the fourth times 1 minus 0.9 to the third. So now let's see if we can go back and arrive at an answer for our original question here. The chance that I make exactly 4 shots. Well, there's several ways I could do that, right? It's the probability that I make, and then miss, miss, miss. Or that I make, miss, miss, right? Okay, sort of ran off the page there. Sorry about that. Or that I make, miss, miss, right? Or, and so on and so on. Now, these are all disjoint events, right? That is, this event is mutually exclusive of this one. And they're both disjoint, from this one. For example, it's not possible, if I'm going to make 7 shots, I cannot possibly make the first 4 and miss the last 3, and say make the first 2 and miss the third and fourth, right? Here you have a conflict. Third and fourth are being missed, and here you have the third and fourth are being made. See, each one of these strings of 7 things there is an outcome. That's an outcome. This is an outcome of this experiment when I run these 7 trials. This is another different possible outcome when I make these 7 attempts. Okay, I've got all these different outcomes here. They are all disjoint. So by axiom 3, I can write this as the sum of all those probabilities, right? It's the probability that I make, miss, plus the probability that I make, or miss, miss, right? And then plus the probability, of this one here, which is that I make, miss, make. I've got an extra miss on there, don't I? I'm only supposed to miss it 3 times, so sorry about that. I'll change the last one to a make, and plus, and so on and so on. But I've already worked out each one of these, right? I've already determined that the probability for each one of these terms is 0.9 to the fourth times 1 minus 0.9 to the third. It's the same for all of these probabilities. So now to arrive at my final answer, all I need to do is note that it's going to be, the answer is 0.9 to the fourth times 1 minus 0.9 to the third, and then times the number of terms there. Well, how many terms do I have there? Well, the question you just got to ask yourself is, okay, amongst 7 shots, how many different ways can I arrange 4 makes and 3 misses? 4 makes and 3 misses? That's like saying, okay, I've got 7 shots. How many ways can I arrange the makes in there? Because the others are going to be misses, okay, by default. Okay, if I've got 4 makes in and amongst 7, I've got 7 positions. I need to choose 4 of these 7, choose 4 places, choose 4 from 7 to put the makes. That's my final answer. Gosh, I can do this with my calculator. It's going to be 7, choose 4, I'll put that in parentheses, 7, choose 4 times 0.9 to the fourth times 1 minus 0.9 raised to the third. You get 0.02296 approximately. 0.02296. 2.29635 really. Okay, so it's about 2.3%. About 2.3%. See how I did that? Now that's pretty involved. But I think if you look at the formula that we have here in the slides, you'll see that it looks a lot like what we arrived at there. If I define my random variable, this binomial thing, which counts the number of successes in, say, n trials, okay, then the probability that I see little x number of successes, look, it's just like this. I have the total number of trials here, choose little x, the number of successes, and then I take the success probability and raise it to the power of x, and then 1 minus the success probability is the failure probability, right? And I raise that to the n minus x, because n minus x will be the number of failures. The number of successes, x, plus the number of failures, n minus x, equals n, the total number. Okay, so you see, if you compare this formula with what we've written right over here, you'll see that this stuff right in here is just a special case of that formula, where I've got n is 7 trials, 4, that's the number of successes we're looking for, and then 0.9 is our success probability. Okay, bi meaning two possible outcomes. Okay, x is said to be a binomial random variable with parameters n and p if it models the number of successes that occur in n independent trials, where each trial is a success with probability p and a failure with probability 1 minus p. Okay, and so this is how you can count those. This is how you can calculate the probabilities of those successes. Let's answer the rest of these here. What's the chance that Matt makes at least 2? The chance that makes at least 2 of them. Okay, well, again, my random variable here is still x, so I'm interested in the chance that x is at least 2. Gosh, so that's going to be the chance that x equals 2 plus the chance x equals 3 plus, and on, plus the chance that x equals 7. Goodness gracious, that's a lot of work. I don't think I want to do it that way. I mean, that's all correct, but it just takes too much time. I'm going to start with the rule for complements. I think that'll be easier for me. 1 minus the chance that x is less or equal to 1, right? See, I'll either get at least 2 baskets or I'll get 1 or less. So this event right in here and this event right in here are complements, right? I'm using the rule for complements here. And so now I'll take 1 minus. Now what's the probability that x is less or equal to 1? That's the probability that x equals 0 plus the probability that x equals 1, right? Okay, so I can do that now using my binomial probability formula. Okay, so that'll be 1 minus bracket. What's the chance x equals 0? Let's see. Got 7 trials. I'm looking at getting no successes. 0.9 raised to the no successes, right? 0 successes times 1 minus 0.9 raised to the 7th. That's the number of failures there, right? We're talking about failing every time. Plus the chance that x equals 1. Let's see. Following the formula, 7 choose 1 times 0.9 to the 1 times 1 minus 0.9 to the 7 minus 1 is 6. Okay, and then I'll put all that into my calculator. I get 1 minus quantity, 7 choose 0. Hey, what's 7 choose 0? How many ways can you choose nothing from something? There's only one way. You just stand there and choose nothing. There's one way to do nothing. There's just one way to do nothing. Actually, that's not true. I've invented all kinds of ways to do nothing. But anyway, that's another story. So I take this, multiply by the chance of success, which is 0.9, raised to the 0, times quantity 1 minus 0.9. Whoops. Got to get that stuff out of the exponent there, Matt. It's not where it goes. Okay, I get down out of the exponent by pressing this little right arrow key there. Okay, so times 1 minus 0.9 raised to the 7th. Okay, hop down out of the upstairs, plus 7 choose 1. How many ways can I choose one thing from 7? Oh, there's 7 ways. There's just 7 things. I'm going to pick one. How many different ways can I just pick one thing? That's 7. Do it like that, times 0.9 to the 1 times 1 minus 0.9 raised to the 6th. Okay, hop down out of the upstairs there, close up the parenthesis. I hope that's correct. 0.99999. Now, whenever I do some of these problems, I like to go back to the original question, see if the answer makes some sense. The chance that I get at least 2 should be pretty high, right? Because I've got a pretty good chance of making any one shot. It's 90%, right? So if I'm going to take 7 shots, what's What's the chance that I make 1 or less? That's pretty small, right? Should be. What's the chance that I make no more than 1? No more than 1. Hey, we've already answered that question. Probability that x is no more than 1 is the chance that x is less or equal to 1. It's just 1 minus 0.99999, which is small. Okay? That's what that is. That's something small. Now it's, what is that? 0.00001. Okay. Now let me show you something. I'll come back and talk about the mean and the standard deviation here in a minute. But jump down here to these formulas. This is why you pay the big bucks for your calculator, right? Because it turns out you can compute these probabilities real fast. Your calculator has some really nice built-in functionality. All you got to remember is the P and the C are different. P and C are different. You see, this is binomial PDF, stands for binomial probability density function, and this one down here is binomial CDF, stands for binomial cumulative distribution function. Okay, they take the same arguments, but this first one here finds the chance that your random variable equals x. So like the chance that you make exactly 4, or the chance that you make exactly 6, or the chance that you make exactly 1, or whatever. However, oftentimes we're not concerned with that. Maybe we want to know the chance that we make less or equal to some number. Okay, so let's see how we could have done these with our calculator that way. Okay, for example, when I did the chance that x equals 4, I could have done it like this. I could have used my calculator and said that this stuff is equal to binomial PDF. Number of trials is 7, and P is the success probability, 0.9, and then exactly 4. You see that? Okay. And what does that spell? Let's see, where is that stuff? I tell you what, it's in the distribution menu, which is right here. You see the DISTR here right above the vars key. So I press second, distribution. There we go. And now arrow down until I see binomial PDF or binomial CDF. There they are. Binomial PDF is option A in my calculator. Binomial CDF is option B in my calculator. I want option A, binomial PDF, okay, because I've got the equal sign. I'm doing 7 trials. My success probability is 0.9, and then I want to know the chance that I see exactly 4, and then there we go. Voila, it's exactly what we got. 2.29635%. Okay? 2.29635%, or 0.022965. What about one of these others, like the chance that say x is less or equal to 1? Okay, well, I could do it like this. The chance that x is less or equal to 1. This, I'm going to use binomial CDF. The C is for cumulative, okay? Cumulative. Because you accumulate, you add up. Cumulative. Okay, that's what that's for. Okay, so whenever you see this sign here, you want to, or even the greater than or equal to sign, or the greater than sign, you want to use this function. Okay, and you want to use this kind of function. Now you got to be careful though. If you see the sign go this way, you got to use the rule for complements. I'll show you in a second. But if you see the sign going this way, then you can straight off just use binomial CDF, and this is what you do. Binomial CDF. Let's see, we still got 7 trials. My success probability is 0.9. And I want to know the chance I see less or equal to 1, so I'll put a 1 right there. I'll go over to my calculator, and what do? Hey, that's in the same menu as the other one, right? So, whoops, I press second, vars, and I'll go to where I see binomial CDF, which is here. 7 trials, success probability is 90%, and my x value is 1, right? I know the chance I see less or equal to 1. Paste that in. Whoops, I did something crazy and put it in the wrong place. So let me try that again. Go to distribution, go down to where I see binomial CDF. There it is. And 7 trials, 90% chance. My x value is 1 in this case because I want to know the chance that I see less or equal to 1. Go paste, and yeah, 6.4 times 10 to the negative 6th. Okay, so I guess maybe we rounded a little bit before. Okay. 6.4 times 10 to the negative 6. That's what that means. 6.4 e minus 6. E here I think stands for engineers. This is engineering notation. This over here is scientific notation. Either way, it means 6.4 parts in 1 million, right? 10 to the negative 6 is 1 per million. Okay, so then if I wanted to see, the chance that x is, say, at least 2, well, that's when I need to use the rule for complements. Note that this is 1 minus the chance that x is less or equal to 1, which would then be 1 minus binom CDF 7 comma 0.9 comma 1, okay, which works out to be 1 minus 6.4 times 10 to the negative 6th, which is, if I take 1 minus the answer there, 0.9999936, okay, which is what we got before. Remember, we just rounded, okay, this number was actually rounded. It was, there should be a 3/6 there, okay? Again, real important here, you'll want to use your calculator, use these functions to get these kinds of probabilities. Pay real careful attention to these signs, right? If you have an equal sign in there, then you use binom PDF, okay? If you have a less or equal to sign there, then you use binom CDF. And if you have a greater than or equal to sign there, then you need to use the rule for complements and then also the binom CDF function. Now, what about the mean and standard deviation for binomial random variables? Well, it turns out, we have this general way of finding means for, for general random variables in general, right? Like if I have some random variable x, its expected value, or mean, is just take the values it can take on times the probabilities, right? Like that. Add those products up. In the case of binomial, if x is binomial with parameters n and p, its expected value or mean, well, what do? You fill in. I could say little x goes from 0 up to n, right? Put an x there, and then multiply by the probabilities. What do the probabilities look like? N choose x times p to the x times 1 minus p to the n minus x, right? It's because these are the binomial probabilities. That's the form of them. Now you can prove using math and stuff. All this stuff works out really nicely. It simplifies. Take some algebra. It's not too bad, but we're not going to do it. You can look it up online if you want. Just n times p. And that makes a lot of intuitive sense if you think about it. Hey, if I'm 90% from the free throw line and I'm about to take 7 shots, then how many do you expect me to make? Well, 90% means times 90% of those 7 shots, right? 7 here is my n, and p here is my 90% there, okay? Which works out to be 6.3, okay? You'd expect, on average, for me to make 6.3 shots. Now, don't feel compelled to round this. Don't say, oh, this is equal to 6. No. Don't do that. Leave it alone. It's just fine. What this means is if I woke up every morning for the rest of my really, really long life and took 7 shots from the free throw line, they were all independent and made them all with probability 90%, then on the average, I would make 6.3 of those shots per day. Now, I'd never make exactly 6.3 shots, of course, because it's a discrete variable. I'd make 7 some days. I'd make 6 some days. Some days I'd make 2. Some days I'd make none. Very rarely would I make none, but occasionally. But on the average, my long run rate at which I make shots is 6.3 per day. Similarly, it turns out there's a nice little expression for the standard deviation of a binomial random variable. And we're not going to work this out, but it turns out if x is a binomial random variable, and again, you should remind yourself, quiz yourself on what this means. It's a binomial random variable if it tracks the number of successes that occur in n independent trials, where each trial is a success with probability p. Okay, if x is one of these things, say with parameters n and p, then the expected value of x, also, sometimes again we write mu and maybe we'll put a little x down, or a big X down there in the subscript to indicate that we're talking about the mean of x, turns out to be the number of trials times the success probability. And the standard deviation of x, it turns out, there's a nice succinct little formula for it. It's the square root of n times p times 1 minus p. Okay, that's great. So you don't have to use that long formula for standard deviation in general. Okay, so in the case of our basketball example, the mean, we know it turned out to be 6.3, right? Because it's 7 shots times 90%. And the standard deviation of x is going to be the square root of 7 times 0.9 times 1 minus 0.9. 1 minus 0.9 is a tenth, right? So can I just do that? So I take the square root of 7 times 0.9 times 0.1, okay, it's 0.7937 or so. Now, real quick, what do binomial distributions look like? Pull Many tab over here, and we can see. Maybe I'll try simulating a little bit here, and calculate some random data from a binomial distribution. Okay, remember we talked about using computers to simulate? Maybe I'll do this 100,000 times, because anytime you want to simulate something, anytime you want to check on the behavior of something by simulating, you want to do it a whole bunch of times, right? If you want to know something about the behavior of anything at all, you observe it not just once or twice, but maybe 1,000,000 times, or 100,000 or 1,000 times. I'll put this stuff in column 1. Let's say we're doing 7 trials and I'm 90% from the line. There we go. One time I took 7 shots, I made all of them. The next time I took 7 shots, I made 6. The next time I made 6. The next time I took 7 shots, I made 7. The next time I took 7 shots, I made 6. The next time I made 5, and so forth and so on. So if I make a histogram of all of that stuff there in column 1, you'll see an approximate behavior distribution for this random variable. And I say approximate because we've done it 100,000 times. Yeah, so you see most of the time you see 7, and then some 6s and 5s and 4s and 3s and 2s. And in fact, in this simulation, I didn't see any 1s or 0s. In 100,000 days, if I took 7 shots a day, on no days did I get 0, and on no days did I get 1. Okay. What if I change some of these parameters a little bit? See what happens here. What if I say, let's calculate some random data again from a binomial, and we'll store this stuff in column 2. What if I took more like 40 shots a day, and I'm still 90% from the line? Now I'm going to see, X is somewhere between 0 and 40. I'm going to have anywhere from 0 to 40 successes. Okay. And now let's make a histogram of that stuff. What is it going to look like? Well, this may or may not be surprising to you, but it looks a little more bell-shaped. How about that? It's kind of left skewed, isn't it? In fact, what happens if I do yet another simulation, but this time maybe each day I take 100 shots, okay? Or maybe 150 shots, okay? I'm still 90% from the line, and I make a histogram of that stuff. Wow, it's starting to look pretty normal, isn't it? Nice and bell-shapy. Yeah, it turns out when you have binomial random variables, as your number of trials increases, and as long as your success probability isn't too high or too low, then yeah, you start to see this bell-shaped behavior. In fact, if you fix your success probability, it can be super high. It can be super low. It can be super low. It doesn't matter. If you fix it, keep it in place, as you increase the number of trials, you'll start seeing the distribution behave more and more bell-shapy. And that's exactly what we're going to talk about next.